In this video, we're going to talk about related rates. Related rates problems involve a number of quantities that are changing. The quantities are related to each other, and we know the rate of change of all the quantities except for one. And the goal is to find the rate of change of that last quantity. The computations are similar to what we did last time with implicit differentiation, and you'll see that as we go. So let me do an example, and you'll understand better what that means. Let's say we have a rectangle, and we're stretching it out in both directions. So its length is getting larger and its width is getting larger. And here's the rate of change of the length, 8 centimeters per second. Here's the rate of change of the width, 3 centimeters per second. The question says, at what rate is the area of the rectangle increasing? So we have three related quantities, length and width and area, and we know how those are related. So if I call length L and W will be width and A is area, then A is L times W. So there's a relationship between the three quantities. I know the rates of change of two out of the three, L and W, and the question asks me for the rate of change of A. Now you might think that since the rate of change of length and width are both constant, length is increasing at 8 all the time and width by 3 all the time, that area would also increase at a constant rate, but that's actually not true. The rate of change of area depends on the length and width, as well as the rates of change of length and width. So that's what this last little phrase is for. What is the rate of change of area when the length is 20 and the width is 10? Okay, so we'll come back to that in a minute. Here's our formula now. This is a relationship between the quantities. All three of these are functions of time, which I'll call t. Now, normally I don't specifically note that. I don't put A of t equals L of t times W of t, but in the back of my head I remember that these are all functions of time. So if I use the derivative notation for that rate of change, the derivative of L with respect to t is 8 centimeters per second. The rate of change of W is the derivative of W with respect to t, that's 3. The question asks me to find dA dt. The idea here is to take the derivative of this equation that relates the quantities with respect to t. And that's where this sort of implicit differentiation type of calculation comes in. We have to tell Sage that L, W, and A are functions of t, and then we can take the derivative. Now, look at this caution. This is one of the biggest issues in related rates. One of the most common mistakes students make is you're going to be tempted to take values of variables that are given in the question and plug them in right at the beginning. So in this example, remember we had length is 20, width is 10. You think, okay, great, 20 and 10, we'll put them in right now. 20 times 10, that's 200. So A equals 200. Now let's go take the derivative. And what are you going to do if you take the derivative of the equation A equals 200? You're going to get derivative of A equals 0, because 200 is a constant, it's a number. Is that what you want? No, that's definitely not what you want. So L and W are changing. You cannot plug in the values of variables until after you've taken the derivative. Okay, so we're going to take the derivative of this equation just like it is. So here's how to do that in Sage. Tell Sage first t is a variable, then you need to tell it that L is a function of t, W is a function of t, A is a function of t. We learned about this little function command last time with implicit differentiation. Now that all of these are functions of t, we can take the derivative of our equation, A equals L times W. Remember, two equal signs in an equation. And then comma t here, it says that derivative is with respect to t. And then I went ahead and used show so it looks a little nicer. There's the answer. Remember that little kind of curly d thing we saw last time? You should replace it in your mind just with a regular d. This is just the regular derivative with respect to t. So this says the derivative of A is W times the derivative of L plus L times the derivative of W. Now, normally, we don't worry about this whole function notation, the of t part. Remember, this is not times t. This is not A times t. That's A of t. It's a function. Normally, we just write it this way. Everything in sight in a related rates problem is a function of time, and so we normally don't bother making that function explicit. So dA dt is W times dL dt plus L times dW dt. Now you can use prime notation if you want, just so long as you remember that that prime means derivative with respect to t. So you could put a prime equals wl prime plus lw prime if you wanted to. So this formula now gives us the rate of change of area in terms of w and the rate of change of L and the rate of change of w. Those are things we know. The question gives us these two rates of change for L and w, and the question also specifies a particular w and a particular L that we can now plug in. Okay, so let's start plugging in values. Take L is 20 and put it in this formula. Right, there's L is 20. W is 10, so it goes in right there. The derivative of L is 8, so there's 8 right there. The derivative of W is 3, so there's 3 right there. Just put in the numbers and now calculate. So here's the calculation if you want to in Sage. Now, there's no solve here going on in this example. We're just calculating the numbers. Everything is on the right side. We just need to plug in the numbers and calculate. So it turns out to be 140. So at the specific moment in time, when L is 20 and W is 10, the area is changing at a rate of 140 square centimeters per second. All right, let's do a second example. I have a ladder that's 12 meters long. It's resting on the horizontal ground, leaning against a vertical wall. Well, let's look at the picture. Here's the picture of it. So here's the wall, straight up and down. Here's the ground, horizontal. The reason I make a big deal of that is because I want a right angle here. This is the ladder leaning against the wall, so I have a right triangle. That's going to be important in solving this one. What we're going to do with this ladder is we're going to grab on right down here. It takes my hand and grab the bottom of the ladder and pull this way, away from the wall. And when you do that, of course, the top has to fall down the wall. So I'm going to tell you how fast we pull it away. We're going to grab the bottom of the ladder and pull it away from the wall at 1/10 of a meter per second. And the question is, how fast is the top sliding down the wall? Now you might think that if I pulled the bottom away at a constant rate, the top would fall down at a constant rate, but it actually doesn't. It depends on the angle here this ladder makes with the ground as to how fast this is going to fall down. So I'm going to specify a specific moment in time by telling you that I want to know the rate of change that the top is sliding down the wall at the particular time when the foot is 4 meters from the wall. So I've called that distance between the wall and the bottom of the ladder, I called that x, and the distance from the ground up until the top of the ladder I called y. So this is asking for the rate of change of y, dy dt, at the particular moment in time when x is 4. That's what this information is asking. Okay, so I set up my variables, x and y. I'm told the rate of change of x is 1/10. I want to know dy dt when x is 4. I need a relationship between x and y to do this, and since we have a right triangle, the Pythagorean theorem relates x and y. X squared plus y squared equals 12 squared. Now, notice that I put 12 in here for the length of the ladder. That's because 12 is a constant. The length of the ladder is not changing. So I can plug in constants at the beginning. I don't need another variable here. The ladder is not a variable. It's always 12. So this is different from the last example where we had the length is 20 and the width is 10. Those I had to plug in after I did the derivative. But the ladder I can plug in now. The 12 is fine here because 12 isn't changing. X and y are changing. You cannot plug in the x equals 4 because x is a variable, x is changing. X equals 4 is a specific value of that variable which you can plug in after taking the derivative. So carefully distinguish between x is 4, which is a particular value of the variable, and 12, which is a constant. It's not a variable. Okay, well, here's the calculations. So I declared t to be a variable. I told Sage that x is a function of t and y is a function of t. I took the derivative of my Pythagorean theorem, x squared plus y squared equal 12 squared, comma t, derivative with respect to t. Here's the answer. Sage tells me it's 2 times x times the derivative of x plus 2 times y times the derivative of y equals 0. And hopefully you can see the chain rule in that. Remember, x and y are both functions of t. This is the derivative with respect to t, not x. So chain rule says take the derivative of the squared, which is 2 times whatever, 2 times x in this case, multiply by the derivative of the inside function. Remember, x is a function. This is composition. Y is a function. inside a square function, so you get 2 times y times the derivative of y. That's just the chain rule there. Here's how I would normally write that. Now, we want to have dy dt. That's what the question asks us for. So dy dt is here. Let's go ahead and solve for that. We can have Sage do it for us. So here I did it. Solve. What I'm going to solve? I'm going to solve this equation. What's that equation? That equation was the derivative of my Pythagorean theorem. So this derivative is an equation which I want to solve. I want to solve that for the derivative of y. So I'm going to put comma, solve for the derivative of y. And here's the answer. The derivative of y is negative x times the derivative of x divided by y. And remember, this is not x times t, that's x of t, a function. Or here's kind of more simplified how I'd write it. Derivative of y is negative x divided by y times the derivative of x. Now I'm told I want the derivative of y when x is 4. So I got x is 4. I can plug that in now. The derivative of x, I'm told, is 1/10. I can plug that in now. I need y. That wasn't given in the problem, but I have a relationship between x and y. When x is 4, what is y? Well, x and y satisfy the Pythagorean theorem. So if I put x is 4 into my Pythagorean theorem, I can solve that for y. So I had Sage do it. And here's the 2 answers. Now y is a distance, so I don't care about negative y's. That doesn't make sense in this application. So this is the answer that I want. When x is 4, y is 8 times the square root of 2. Now I'm ready to plug into this formula up here. X is 4, y is 8 square root of 2, dx dt is 1/10, and so I get dy dt is negative 0.0354 roughly. Notice that dy dt is negative because that distance is decreasing. As the top of the ladder slides down the wall, y is getting smaller, and so the derivative should be negative. Alright, let's do a third example. Suppose we have a cylindrical tank standing upright with one circular base on the ground. So here's the picture. I got my cylinder, its circular base is on the ground and standing upright. The radius of this cylindrical tank is 20 centimeters. So here I have r is 20. That's a constant, that's not changing. How fast does the water level in the tank drop when the water is being drained at a rate of 25 cubic centimeters per second? Okay, now notice that 25 cubic centimeters per second is a rate of change of volume. So you got to imagine having a little drain here at the bottom and water is squirting out of the bottom. This is the change in the volume of the water. And I want to know how fast the water level drops. So the water is here, and as the water drains out, the water level goes down. So H is decreasing here. All right, well, let's try to relate all these quantities. So the relationship between the volume and the radius and the height we know from geometry. Here's the formula for the volume of a cylinder. Pi times r squared times h. And we know what r is. R is 20. That's not changing. So we can plug that in right now. Okay, you can put in constants at the beginning. So plug in r is 20 and you get this formula. That relates volume to the water level h. And now we're ready to take the derivative. Alright, t is a variable, v is a function of t, h is a function of t. Take the derivative of v equals 400 pi h with respect to t. This is what we get. Derivative of v is 400 pi times derivative of h. Okay, now we want the derivative of h. That's what the question asks us for. We could have Sage solve this equation for us, though it's really not that hard to solve. You just divide both sides by 400 pi. So the derivative of h is the derivative of v divided by 400 pi. We're told the derivative of v is negative 25. Negative because the volume is going down. It's decreasing. So when something's decreasing, its derivative should be negative. And that gives us roughly negative 0.02 as the rate of change of the water level. Okay, and again, that's dropping, so we should have a negative derivative for that decreasing quantity. And those are some related rates examples. The hardest part about these is really converting the words. Here's the question. Converting all these words into meaningful formulas. I would suggest drawing a picture If you have some geometric shape going on, draw a picture, create some meaningful variable names, label your picture, come up with some formulas from geometry, and take the derivative, plug in the numbers, and that's it.